This is lecture 3, that is for today's lecture, and I have to confess that this topic is going to be a little complicated, but with if you go over them a couple of times, you will probably understand this, and you can correlate that to what is really happening in the real world and understand why exactly something is happening, especially regarding material deformation, and correlate that to what is happening at the microstructural and atomic level. So, we talked about different types of dislocations and the energy associated with dislocations and why um, something deforms at a much lower shear stress levels than what you might actually theoretically calculate, and that is because of the um, energy that is associated with dislocations, and this is correlated to the shear strain and shear stress of dislocations. For a shear dislocation, just take it as a given. I mean, I'm not going to derive these things, but for a screw dislocation, the shear strain and for shear, um, you can see that it is at an angle and at a distance in 3D space. So that is calculated to be equal to B, which is the Burgers vector of the dislocation, divided by 2 pi r, where r is the distance from the origin of the Cartesian coordinates that you are assuming. And the shear stress that is associated with a shear, I mean, for a screw dislocation is equal to the shear modulus times the shear strain, which is equal to the shear modulus times B over 2 pi r. And the other stress components have been calculated or have been derived to be equal to 0. And there is a limiting distance r beyond which this equation will not hold good. So you have a region of shear strain and shear stress around a dislocation where you need to be able to overcome that in order to be able to move that dislocation from one point of the crystal lattice to another point in the crystal lattice. And it has been derived that the stress fields around dislocations are a little bit more complicated and in rectangular coordinates. And just to remind you, for a screw dislocation, because it is in three-dimensional space, it is easier for us to uh, derive that, or having derived that in terms of the uh, the angle and the distance from the origin. But in the case of edge dislocation, you can do that in terms of rectangular coordinates x, y, and z, and so you can derive um, the stresses in around the edge dislocation in terms of sigma xx, sigma yy, and tau xy. And this is a little bit complicated, but you can see that it contains the shear modulus and the Poisson's ratio. So it's actually based on um, based on integration of the stresses around a volume. So for uh, the the elastic strain energy of a screw dislocation has been calculated to be equal to in terms of um, shear modulus times the square of the Burgers vector and multiplied by natural log, and R1 is the position where you are looking at the screw dislocation, divided by R0, where R0 uh, is a standard number. Okay, so it's the origin, or small distance around the uh, screw dislocation. And in terms of edge dislocation, also elastic strain energy, also it can be calculated. So what you have to do is, in order for you to be moving these dislocations so that you can deform the crystal, you have to overcome this elastic strain energy. Then only the crystal will start deforming. And as I said to you, a dislocation is, in the real world, is neither completely screw type or completely edge type. They have both edge and screw components. But in for for calculation purposes, so you saw that this is uh, in terms of this, but when it comes to um, a single dislocation, you can consider that E is equal to alpha times G times B squared, where E is the energy of any dislocation and alpha is a geometric factor between half and 1. Most of the time we assume that is equal to 1. So E is equal to, most of the time we assume that it is approximately equal to GB squared. So which is what we saw in the previous lecture, at the end of previous lecture. So the important consequence of this is that slip will occur in closed pack directions because B is minimum for those types of planes. So which means that they have the least amount of elastic strain energy. Okay, and so that it will be easy for you to move the dislocations and deform the crystal. The other properties of dislocations are, you have, suppose you have a dislocation between um, two atomic positions. There is a line tension of this dislocation, and that line tension will act to straighten the dislocation line and lower the lower overall energy of the crystal, which means that it might be a curved type of a line. And you can see that in the when you look at the crystal structure under the microscope and things like that, you will see a line that is kind of a zigzag type of a thing, which is actually a dislocation. Um, and it will be easy for you to move those dislocations from one point to another when you are deforming the crystal. And as I said to you, it is proportional to GB squared, or it is also equal to uh, the tension and the tau, or the shear force, is proportional to T times T over B times R, where R is the radius of that line or the length of that line. And so you need a force needed to move the dislocation through the lattice. When you combine that, you have the um, the shear force or shear strength is proportional to GB times R. And I know that this probably doesn't make much sense to you, but what uh, you have to know is that there are forces acting on dislocations, and you can move them from one point to another depending upon the force um, you are making the, I mean, how much force you are applying on that crystal. And it depends upon the resistance of the dislocation movement through a lattice. So suppose you have those crystal lattices that are really tightly bound together. You will need, and or if you have a crystal lattice that is very open and um, open type of a structure, you will need much less force to deform the open structure rather than a tightly bound structure. And that depends upon what is called Pearls-Navarro stress. And Pearls-Navarro stress, the name comes from the two people who discovered this phenomenon or derived this phenomenon. Okay, and then what they also found is that force also is dependent on the interactions and the presence of other dislocations. Now, you are not going to have one dislocation alone. You are going to have a multiplicity of dislocations. And so, which means that suppose, if you are just one single person in a room, okay, you can easily move through that room. But suppose there are 1,000 people in this room, you have to make your way through the whole um, crowd, right? So the same way, if dislocations have to be moved, you have to take into consideration that those dislocations are going to interact with other dislocations, which means that they can either be repelled or attracted. And how do you know that? So in the case of screw dislocations, they are much easier to understand. They always repel each other when the Burgers vector sign is the same, and they will always attract each other when the Burgers vector sign is opposite. And where does this come into picture? I mean, I think we had in one of the earlier images, I think it's not here in this one, but in the earlier image you saw that um, the edge dislocation is um, you have a half plane, extra half plane, right? So there could be an edge dislocation that is exactly the reverse of that. So when you move that edge dislocation such that they come towards each other, that extra half plane will cancel out each other and become a full plane. So the whole edge dislocation will disappear. Same way, if screw dislocations are there, so you have um, a part of a crystal that has been deformed in a certain way, and a part of a crystal has been deformed in the opposite, exactly mirror image of this dislocation. And if they are being moved in a way that they attract each other and combine each other, that means that the two screw dislocations will cancel out and become a perfect crystal. Okay, so, and in that case, one part of the dislocation, one screw dislocation like this has got one Burgers vector sign, and this one has got another Burgers vector sign. I mean, this is opposite Burgers vector sign. So when you combine the two together, they will attract each other and cancel out each other. But if they are the same way, then they will rather repel each other. And the case of edge dislocations is more complicated. So you can look at the forces between dislocations. So this is the schematic representation of that. So it depends upon, so if there is a optimum distance between them, where the force is the minimum. So um, 1 y, where y would be the equal to the distance between the planes. So if they are one atomic plane away from each other, they have the least amount of force. But the closer they are, there is a lot of force, and it makes it very hard for those dislocations to start moving. Okay, so this is all listed here, and in order for these dislocations or the combined movement of atoms is called slip. So which means that you have a whole set of dislocations moving, and in the case of uh, slip, which is deformation of atomic planes. So if you have only edge dislocations, the the type of dislocation, edge dislocation, the slip direction is parallel to the Burgers vector, and in the case of screw dislocation, it is uh, also parallel to the Burgers vector, but the dislocation line and the Burgers vector is perpendicular and parallel. So they are both opposite to each other. So I know that this could be a little confusing, but you have access to these. If I ask you a question, you have access to this uh, table, so you should be able to answer those questions. So if you have dislocations in one single plane, if you have edge dislocations, they would rather uh, move by the process of non-conservative climb, which means that you have to provide extra energy through heating so that the atoms can diffuse from one point of the lattice to another. And in the case of the screw dislocation, they have to move from one level of the plane to another. So it is called cross slip. So these are the two ways in which um, the different types of dislocations can move. So that's what is going to cause this whole crystal lattice to deform. Please go over this a couple of times so that you understand the whole concept of this class. So what is the other way in which dislocations can move? Now suppose you are trying to run from one point on a field to another. If there is nothing stopping you, you can just glide past everything. But suppose you have suddenly you have a wall in between, so your movement will be stopped. So the dislocations can be stopped by the presence of grain boundaries or other atoms or atomic planes. But even then, those dislocations can move. How do you do that? So think about um, what is that Arnold Schwarzenegger movie? Think about that. Okay, the Terminator movie. So these dislocations will become like Terminator. They dissociate into two dislocations, then they start moving in parallel to each other, and then they combine and again move. Okay, because the reason is that the elastic energy of the partial dislocations are lesser than that of a single dislocation, and you can actually calculate uh, the elastic strain energy of the partials. So the elastic strain energy of the single dislocation is greater than that of the partials. So that's why it becomes easier for those dislocations to dissociate and then later on combine into one again and then start moving again. Okay, and how does that happen? So this is how it happens. So you can think of these as atom positions. So I don't know how much you remember this from your ENSE 3313. So the FCC is the atom positions are called ABC ABC. So how is that? So this is one plane, and the next plane the atoms are located on top of these holes at the bottom plane. And then the third one is it goes over the even the top one. So the holes in this position are not the same as the holes in the lowermost position. So that's why it is called, so this A, um, plane A is not the same as plane C. So the atom positions are all different, okay, for the case of the face-centered cubic. So they are called ABC ABC type of crystal um, structure. In the case of hexagonal close packed, they are located on top of this, but they are slightly tilted in a way. And then the third one again falls right on top of the, the first layer. So which means that it is a AB type of structure. Okay, so depending upon that, you can calculate the amount of force that is required for you to move these atom planes. So if you have a dislocation that is moving in this plane of atoms, okay, so I realize it is a little difficult for you to conceptualize the whole thing, but just understand that it is easy for you to move these atom planes from one point to another, and the force required to move these atom planes are different. So suppose there is a dislocation or um, crystal defect is moving from one point in this crystal lattice to another, and it comes up and hits up against a location where it cannot move those atoms at all. So it will kind of go around this atom wall, atomic wall, and then join up and then start moving again. So then it becomes easier for you to move these atomic uh, planes and atoms. So that's what is the whole concept of dissociation of these dislocations. Okay, so this is for the hexagonal close packed, and you can actually, I know that it is not very easy for you to conceptualize. So all you're doing is you're moving these different atomic planes from one place to another. Okay, so for example, in the FCC unit cell, um, which atom planes are or which atom planes are easy to move? Okay, so you have, so this is the atomic plane which is has the highest atomic density, and they have the widest interplanar spacing. So this particular plane has the maximum distance between the next highest atomic density plane. So these plane of atoms is easiest to move, whereas this one, it will not be easy for you to move. Okay, again, the slip direction is in this, that is also the closest packed directions. Okay, so for the FCC unit cell, it is the interplanar spacing is 111. So this is the plane with the highest atomic density, and the slip direction is 110. So how do you calculate if it is possible for you to dissociate these dislocations? For example, if you have uh, a, a dislocation that is of this type, okay, so you have to calculate um, what is the, how do you sum up the, how do you know if this is possible to sum up or not? And for that you need to calculate, you need to sum up the xyz components of the right hand side, and it should add up to the xyz components of the original dislocation. So in this case, um, the x component is 1/2 is equal to 3 by 6. So I mean, you can, this is bar 1, and this is 2 bar, and this is 1 bar. So half is equal to 3 by 6, which is equal, and in the y component, 0 is equal to 1 by 6 minus 1 by 6 over plus 1 by 6, so that is equal to 0. And in the case of z, it is 1 by 2 is equal to 1 by 6 plus 2 by 6. So it is possible to dissociate this dislocation into this dislocation. Okay, so that is the you will be given these numbers. Okay, so you can actually calculate them based on that. So how do you calculate the strain energy of this particular dissociated um, dislocation or the partial dislocations? So one dislocation is dissociating into two dislocations. So if I give you that, G is the same on both sides. So you can actually calculate, I mean, you can actually cancel out the value of G. But um, so if you square this, B squared is equal to A squared by 4 times 1 plus 1 should be greater than A squared by 36 times 4 times 1 plus 1 plus A squared by 36 into 1 plus 1 plus 4. So you see that this is indeed true. So this holds good. So it is possible for you to dissociate this particular dislocation into two partial dislocations. And how does that happen? I mean, I think it is a little difficult to understand this conceptually, but you can see that it dissociates into a couple of different dislocations. So the lines will dissociate and kind of move around and then join up again. And it is also going to be dependent on the number of dislocations in a given volume in this material. And so, for example, if you have FCC, if it is ABC, 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 so suddenly that ABC will just become BC. Okay, so they just move over to another position and they create a stacking fault. And that stacking fault is actually seen under the microscope as an area of high energy, where this distance is called the d between the partial dislocations, and b1 and b2 and b3 are the partial dislocation Burgers vectors, g is the shear modulus, and gamma is the stacking fault energy. So that partial dislocation separation is calculated to be or derived to be equal to g times b2 into b3 divided by 2 pi gamma. And for every material you have the dislocation separation, which is equal to something called the stacking fault energy. So for each material you can, they have calculated that, and you should be able to find it in handbooks. So if you have ABC, ABC, so that is the stacking sequence of the FCC lattice. And suddenly you are going to be creating the B layer becomes the C layer. So the B layer will slip over and go become the C layer. So now your stacking sequence becomes ABC, AC, ABC, ABC, etc. So suddenly you have a stacking fault. Okay, so B atoms have been put into the C site, and this is called the stacking fault in a lattice. So if you look at this material under the microscope, you can see that this area will suddenly appear to be a dark or a different um, color compared to the other parts of the lattice. And depending upon the distance between that stacking fault areas, you can see that it is easy or difficult to move these dislocations. So some things to note about partial dislocations are that they will repel one another along the slip plane if they are of like sign. Um, and their recombination will lead to removal of uh, they will not remove uh, the dislocation itself. So if you have a partial dislocation in an FCC material, you are actually making a ribbon of hexagonal close pack structure in an FCC structure. And HCP also is close packed. So if you have a partial dislocation in an HCP type of structure, one partial dislocation will create an FCC ribbon of FCC material. And if you have a partial dislocation, they cannot cross slip and they must be made to recombine. And that is difficult if the stacking fault energy is low. And the stacking fault energy is going to be um, dependent on the type of crystal structure. So for example, um, it is said that you can derive this to be the stress required to move these dislocations is equal to a constant times e to the power n, where n is a value between 0.25 to, or it can be anywhere from 0 to 1. Okay, so if it is greater than 0.25, then these there are no partials in BCC. So you can see that a BCC type of material, it is very hard for you to deform a whole lot. You have to make it into a FCC type of structure. So now you can understand why you are heat treating steels from a BCC type of structure at room temperature to FCC type of structure, which is gamma austenite type of structure at elevated temperatures, because it is easier for you to deform the material. And in the case of FCC, the value of N is between 0.25 to 0.55. And if you have cross slip, um, that will limit work hardening. So in the case of BCC, the value of N, the work hardening coefficient is less, um, and you cannot find a way to decompose that uh, original dislocation on a 1 bar 0 plane, so it will be difficult for you to deform the material. Whereas in the case of FCC, it is very easy for you to deform because the work hardening coefficient is pretty high. So you can work harden and get the material to deform very easily. One thing to note is that um, for FCC type of materials, the stacking fault energy is pretty high. So the partials will hardly repel, so they would rather combine and become and deform the material much more. So it is easy for you to deform something like aluminum or something like steel if it is heated to a temperature above 800 degrees centigrade. So if stacking fault energy is low, repulsion is far and recombination difficult. So N is very high. Example FCC. So N in the case of FCC, it is pretty high, around 0.55. So if stacking fault energy is low, that means it is not easy for you to deform the material. If stacking fault energy is high, that means it is easy for you to deform the material. I hope I'm not confusing you, but stacking fault energy high, deformation easy. Stacking fault energy low, deformation difficult. That's all you have to remember. Okay. Um, I think we had talked a little bit about this in the last class. I mean, this is not really related to uh, this. So you can see that if you look at the stress strain curve, so what does this tell you? The BCC. So in this case, it is not very easy for you to work harden BCC. But if you have 304 FCC type of material, um, it is easy for you to deform. The work hardening coefficient is pretty high. Um, so FCC is good for deformability, and it is easy for you to create structures by hot working or cold working, etc. So the combination of, I mean, the comparison of BCC and FCC, one thing to note is that BCC is not very close packed. It is brittle at low temperatures and very high yield strength at room temperature. There are no partial dislocations. You cannot work harden it very easily. It has got lower work hardening coefficient. Therefore, it has got less formability and less weldability. But in the case of FCC, it is the opposite way around. And these are some pictures from the textbook that I added in here for your understanding. So um, again, to re-emphasize, smaller the stacking fault energy, larger the separation between partials, um, which means that it is difficult for you to recombine the partials. Um, in high stacking fault energy, you need very little stress to recombine the partial dislocations. So which means it is very easy for you to work harden that material. How can dislocations interact with each other? So as I told you, if there are two edge dislocations, the one is positive and one is negative, if they are moving towards each other, they can combine and cancel out each other. But if they are of the same sign, they would repel each other and they would not exactly combine between the two. Whereas in the case of, so uh, how else can dislocations move? Say for example, um, if you have edge or screw dislocations that are of the same sign, so then um, they would rather move from one plane to another and then start moving again. So you have to have what is called an edge jog in order to be able to move the dislocation. So, but if there are two screw dislocations, um, they would rather combine two and then they would cancel out each other, or they would rather um, combine with each other. Okay, so you can see this. I mean, so look at the stacking fault energy. So what did I tell you? Stacking fault energy low, which means it is not easy for you to deform the material. Stacking fault energy high, which means that it is easy for you to deform the material. So you can see that brass and stainless steel, they have very low stacking fault energy, so which means it is very difficult for you to deform these two materials. But in the case of nickel, aluminum, etc., they have very high stacking fault energy, which means it is easy for you to deform the material. So how else can you deform the material? You have to be able to multiply the dislocations, and not just multiplying by many times. You have to have, so if you just take a material that has just been annealed, they have a dislocation. So they do have dislocations even in the annealed state. They have dislocations. So that is approximately 10 to the power 4 to 10 to the power 5 dislocations per centimeter squared. But if you cold work the material, you see you are almost doubling the density from 10 to the power 4 to 10 to the power 11 to 10 to the power 12 dislocations per centimeter squared. So you have so many dislocations that have been introduced into the material. And how does that happen? So think about this dislocation as a line between two atoms. So they have been held taut between two atoms. Okay, they are pinned at two ends by obstacles, another dislocation, etc. and what is the force required in order to move that. So that is proportional to GB times R, where um, R is the radius of that line. Okay, so when you start pulling them apart or deforming that material, it starts bowing from one side to the other. And as you apply more and more force, they will start coming together at this end, but they will start becoming a circle around this. So as soon as this comes close to each other, these two dislocations are of opposite Burger's vector signs. So they will cancel out each other and they will become one line. So now you have a single circle around this. So there is a dislocation that has gone out from the inside. What do you do now? Now, when you apply more and more force, now this line starts bowing out each other, and then again it will create another uh, circle, and become equal. Um, I'm sorry, I cannot see this, what is going on. Um, Let me, I have to close this out and start again.